Hi, my name is Anna Mikkelsen, and I'm a researcher at the University of Minnesota in the Center for Sustainable Polymers. I'm here today to talk about self-healing the earth through a renewable PLA Vitrimer teaching lab experiment. Before we get into the research, I want to talk about specifically what a Vitrimer is. A Vitrimer is an associative covalent adaptable network, or a CAN, which is a cross-linked polymer or plastic network that undergoes dynamic cross-link exchange when exposed to elevated temperatures. As you can see in the diagram on the right, you have two pink cross-linkers that, when exposed to heat, exchange onto different purple polymer strands. But to put this in more conventional terms, you have two main types of plastics. You have thermoplastics, which are going to be your PET water bottles, and then you have your thermoset plastics, which are going to be your epoxy resins or silicone cooking utensils. And in the middle of the two, you have a Vitrimer or a CAN, which is cross-linked like a thermoset, but unlike a thermoset, is able to be reprocessed due to the dynamic cross-link exchange that occurs. This allows it to have interesting properties when it comes to recyclability. But our main goal in this research was to see if Vitrimer chemistry could be incorporated into a teaching lab. So what I did specifically was I took this two-step synthesis that used L-lactide and pentaerythritol to make a renewable Vitrimer, and substituted out the tin-octanoate as the catalyst, which is toxic, and the toluene and DCM, which are hazardous solvents, for more green substitutes. And the way I did this was I assayed multiple different catalysts to see what would work best, and I ended up finding that bismuth neodecanoate, or bis-neo, was the best option to allow the synthesis to be one pot. In the first step, I was also able to eliminate the toluene, making it a neat synthesis, and also eliminating all purification steps. And then the second step, I was able to substitute DCM for ethyl acetate, which is a green solvent. With all of these changes to these green catalysts and solvents, we were still able to see the cross-linked polymer exhibit vitrimeric properties such as self-healing and strong welding. This is because even with the new catalysts and the new solvents, you still were getting that same dynamic cross-link exchange that we saw in previous literature papers. In conclusion, we successfully made a material that maintained its vitrimeric and mechanical properties while reducing the toxicity and hazardousness of the synthesis. We also demonstrated that a variety of green catalysts can be used for the synthesis and that tin-octanoate is not necessary. We reduced the time and the waste through making this a one-pot synthesis. And hopefully once COVID is over and this can be implemented into a teaching lab, it will expose students to green chemistry and cutting-edge polymer science that they would not normally be exposed to. Additionally, I hope this encourages future researchers to use green and renewable catalysts and solvents. Thank you for listening to my talk. I would like to take a moment to acknowledge and thank the Wissinger Group, specifically Dr. Jane Wissinger and Dr. Jeffrey Buenafor for their continued support. I'd also like to thank the NSF and the Center for Sustainable Polymers for funding this research.